Okay, we want to understand waves. To understand waves, you really got to start with the impulse momentum theorem, which is, of course, essential for the kinetic theory that I assigned, right? Many problems in the existing problem bank. I think I've assigned it. Double check. But we're going to talk about waves. Start to talk about waves. We start with the unit circle. So this is a unit circle. Now, if the circle has radius A, then it would be A times the cosine of theta and A times the sine of theta. And that's your basic definition of your trigonometric functions, which I assume you know. And if you don't know it, you need to know it very well. So you can do this. I'm going to put a unit circle over here. Not a unit circle. I'm going to put a circle of radius A. And I'm just going to draw a series of vectors. Here's the origin that represent the position of a point moving around this circle with a constant angular velocity. Okay. So that theta, which is the angle of wherever you are, here's theta, is a function of t, and it's equal to omega t. Now that's very familiar. If you remember anything that we did with simple harmonic motion, that's the model that I told you you need to really understand. Okay? If you don't really understand it, then really understand it now, because it's the key to understanding the equation of the harmonic wave. Okay? And harmonic waves are about as far as we get to go this time. All right. So you got theta of t equals omega t. Now, over here, I'm going to draw an x-axis. Now, you should be able to tell me, think about it for a second. You don't have to tell me. Normally, if we were on a normal schedule, I haven't missed 2/3 of the classes in the first 3 weeks, I'd let you write it down. I'd let you ponder it. You're just going to have to get it. Okay. So you might think about wanting to go back to the video so you get these fundamentals. Or if you can infer them from the introductory problem set on waves, that's fine too. Okay. But here is what you do. Okay. How long does it take to make a complete circuit here? Can you tell me? Well, you should be able to reason it out, but it's been a couple of months since you had to know it for the exam. Okay. It's either omega over 2 pi or 2 pi over omega. You know which one? That could be confusing. Okay. So I'm just going to say period is the number of seconds divided by the number of cycles. If you go through 20 cycles in 5 seconds, Then how long does each cycle take? That's what the period is. Each cycle takes 4 seconds, right? Well, you get cycles in your denominator. I'm not going to do that. Yeah, okay. Let's do cycles Let's do it right. It's radians per cycle over radians per second, right? Because you divide radians per cycle by radians per second. You get seconds per cycle. Okay. Now, how many radians per cycle? Well, how many radians per cycle? 2 pi radians around the circle, right? And how many radians per second? That's omega. So your period is this. A little easier is frequency, and you might want to start with frequency. Frequency is omega over 2 pi. And you divide that out, and you're going to get cycles per second. Oh, I'm sorry. Yeah. Now, you shouldn't have to remember a formula like T equals 1 over F or F equals 1 over T. If you do have to use that formula, okay. But if you have to use that formula, your brain is going to be cluttered with hundreds of formulas because it's so fundamental. Okay. Frequency is how many times you go around this thing in a unit of time, right? Well, we'll talk about seconds. Okay. So it's cycles per second. And period, as we've seen, is the number of seconds it takes to do a cycle. So that frequency is a reciprocal of period. Okay. Now, the introductory problem sets are going to assume that. I think you start out with several problems that just emphasize that frequency is reciprocal of the period, or periods are reciprocal of the frequency. Get that idea in your head so you don't have to clutter up your minds with a useless formula. But if you need that useful formula, then it's not useless. Okay. If you want to remember by the formula, okay, the formula is there. But you want to see why the formula is what the formula is, and you want to see why the wave forms the way it does. And you'll see a lot of that. Okay. So now, okay, we want to split. And actually, we don't want this to be the x-axis, we want this to be the time axis. We want to split the time axis into periods. Okay. So here is multiples of 2 pi over omega. Now this goes on theoretically infinitely, but I don't have time to write them all. Okay, so we'll just look at the first period here. Now, between here and here, is that a period or less than a period? Well, you've gone less than one time around the circle, so it's less than a period. It's a quarter of a period, right? Okay. So I'll subdivide this period. Now it's 2 pi over omega divided by 4, which is going to be omega over 2. Sorry. Pi over 2 omega. Pi over omega. This is pi over 3 omega. I don't have room to write that down. I just divide this by 4. Okay. Then I divide it by 2 to get this one. And then I multiply 3 times what I got here. I get 3 pi over 2 omega. Now, hopefully, that's not a problem for you. Okay. So I'm going to say that now this occurs here's my t equals 0 position. And here is my t equals 2 pi, pi over 2 omega position. So my reference point moves around the circle at a constant velocity. In the first quarter period, it moves from the t equals 0 position to the t equals pi over 2 omega position, 1/4 of 2 pi over omega, 1/4 of the period. That means we start here. At t equals 0. And we end up here after that quarter period at pi over 2 omega, which is 1/4 of the period. Okay. Then we go around here. I normally ask you to write this down to visualize it. Where am I going to be on the graph? If I go from here to here, I'm going to be down here. And then we go around to here. And where am I? I'm down in my labeling, which is kind of ignorant of me. But we're down. Whoops. Wrong time. And then we're back to our original point. And we've gone through a complete cycle. Now, we follow a straight line from here to here, and then from here to here, and then from here to here. No, because this point here is demonstrably closer to the top than it is to the x-axis. In other words, this point here, if this is t equals pi over omega, this is our half of a quarter cycle. It's like a 45-degree angle. You know the sine of 45 degrees is the square root of 2 over 2, which is about 0.7. And if you don't know that, you're not thinking about the numbers enough when you do everything on paper, okay? And you're not writing it out enough. You haven't been in your life when you do trigonometry. If you don't know that the sine of 45 degrees is the square root of 2 over 2, and that's about 0.7, or more accurately 0.707, and I can't go any more than that, although I know how to figure it out from a Taylor series, okay? But that means that this point is not an accurate point on the graph. You don't have this point because that point is only halfway from here to here. We got a point that's 7/10 of the way from here to here. So it's going to be up like here above this straight line. So you're gonna be going up here pretty linearly, and then you're gonna curve around. And then from that, you're just gonna curve around. You really need to understand that for many reasons, to understand nonlinearity and a whole lot of stuff. So we've just done a cycle of a sine wave. I want you to understand that. And if we keep going around here, well, we're going to keep going through the same points again and again, so that the graph is going to continually do this. Oh man, that was bad. I'm screwing it up, but you get the idea. I keep one name for the wrong point, so that's a badly drawn sine wave, okay? If you're careful, you can draw a better one. And I hate to draw a perfect one the first time because I hate to show off when you think it's achievable that you can do something better than what you see on the board. Very rarely, but it's achievable. You should draw that and think about everything that I've said. All right. Well, that's kind of what happens. If I take the end of a rope, an infinite rope that's somehow suspended, say we've got a bunch of little threads drop down from the ceiling and wiggle the rope back and forth, we're going to get that sine wave traveling on down the rope. Okay? So this is a stationary sine wave. It's maybe the sine wave you get at the beginning of a cycle. Now it's a little confusing maybe, but that sine wave will then travel. Okay. So if I change the phase of this sine wave so that it starts, let's say here instead of here, what's it going to look like? I'm going to draw kind of small and sloppy, since you've already seen it drawn impeccably. So here's my t-axis. And let's say here's my t equals 0. But I start the thing here, let's say t equals 0. Okay. Well, we're going to go around again. But I'm starting here, and I'm starting near the top, so I'm starting here. Here's my initial point. It's not here anymore. Okay. Then we can divide this into quarter cycles, do a couple of them. And I'm going to be here after another quarter cycle and here after another quarter cycle, right? And I'm going to have to go through a whole cycle between here and here. I got to kind of do this. And I'm not going down far enough, and it's not quite right. But that's really badly wrong. I'm not going to take the time to be careful. Okay. Again, compressed time. We're already a week and a half behind as far as class time goes. All right. So you get the idea that the wave is now like this. If we start at t equals 0. Well, this equation of this wave is, let's say, y equals a sine of omega t. And the equation of this wave I'm going to call this angle phi, the Greek letter between phi, pho, and phon. Okay? Everybody knows the Greek alphabet. Phi, phi, pho, phon, I don't know, alpha, beta, upsilon, whatever. Okay. Are we okay? Okay. So that's phi. this is the graph of y equals a times the sine of omega t plus phi. Because I'm starting at phi, and whatever angle I've got is we're still moving around here at omega t, right? So at a typical theta, let's say here is
I say all that to say that f minus one doesn't.
my angle. The angle starting from the positive x-axis is theta equals omega t plus phi. I don't even know if you can read that. I'm sorry about that. Okay, this angle from here all the way around here, should have made a bigger picture, but I didn't. It's omega t plus phi. You spotted phi at the beginning, and now you start moving to omega t. Or maybe this just happens to be where you started observing the thing. Okay. Now, if you want to do y versus x to get the actual shape and space of the wave, it's the same picture. Except that you're not labeling this in terms of time, you're labeling this in terms of how many cycles you've traveled. Okay. So if the wave travels, put this up here, it's going to be a little cockeyed, but you'll be able to see at least the really important part of it.
You say it's six, what it does to apply that, because six is the number. So it's just more or less like the same kind of question I asked it to look like small.
Here's going to be an x-axis. At time t, theta equals and I haven't labeled, I think I want to. Let's leave that alone for a minute. I'm going to label this in periods. Here's x equals 0. Here's x equals capital T. Here's x equals 2 times capital T. Okay. For your period, T equals what? 2 pi over omega. Wave speed, we're going to call C. I'll give you a formula for figuring out what C is in a minute, and we're going to test that with a chain of rubber bands on Friday. It's going to work. Works very well. Wave speed is C. So, I mislabeled X here.
That's why we care about what.
Every cycle, the wave propagates a distance is equal to the period times the speed of the propagation. Just speed and distance, right? So I should have labeled this CT and 2CT. Can you see that? Can you see the C? You believe it's there, even if you can't see it? Okay, that was kind of bonehead on my part. Okay, well, what then happens is, depending on where you are on this circle, we start at some angle theta, which is equal to in general, omega t plus phi, just like here. Okay. Then we move through a complete cycle during every period. So if I start here, that's going to look a lot like the picture I drew previously. You know, this line here, I didn't label before, but it's a line y equals negative a. Now, this line up here is a line y equals a. So our position is going to go between 0 and a. Now, our y coordinate, just like it did here. But instead of labeling in terms of time, we can label in terms of position x, just knowing the speed of propagation. So we would start here. Let's see if I can draw just a little more carefully. A little better angle. And there is a picture of our wave at an instant in time. Now I'm being a little careless with the syntax of my statements. It's gravity. Okay, just so we can say a lot in a fairly short time. So this is a picture of the wave at the instant t. And you want to digest this. You want to digest this picture, and this picture. Now, what would the wave look like at a slightly later instant? Okay, I'm going to run my English section again. My circle radius I. So a little bit later,
very different.
time has moved on, which means that our reference angle here has moved on. Okay? So that we have a picture that looks a whole lot like this picture. Got my labeling in the way, so I'm going to have to start over here. So just imagine that this line is in the same position as this line. Well, in this case, we start here. It would have been clearer if I'd have moved a little further, but we start here. Instead of moving up to X position A here, we're moving down in the Y direction. Should be pretty obvious that if we're over here past the 90-degree position, that and the thing is moving counterclockwise, the reference point is moving counterclockwise, it's now moving downward. So this thing is now moving downward. And it's going to be here. And then here, let's keep this a little bit more horizontal. And then here, a little bit below the top. So it's now moving downward. It's got to come around and it's going to have to hit a peak a little ways before it hits this point. Again, if I get it to do over again, I redraw the diagram a little bit differently. But my peaks are going to occur here and here. So that the wave is going to look like this. Now this looks a whole lot like this, but look at where the peaks are. I've got a peak here, I've got a peak here, you know, I have another peak over here. Now I don't have a peak yet. I don't reach a peak until I get here and here, right? So the wave is shifted. Now, has it shifted to the right or to the left? Point. It shifted to the left because the peaks are curling. They're occurring earlier, not occurring earlier. Okay, peaks are occurring earlier. So this is a model of the wave traveling to the left. Okay. So y equals a sine of omega t plus phi. Represents a sine wave, and it's a sine wave in time or in space. If t is variable and increasing, and omega is positive, then this represents a wave traveling to the left. Every little time increment, it shifts to the left. How far does it shift to the left? Well, I can draw that little increment. Okay, before the peak was here. Okay, well, let's see. Previous peak. Got some green talk here somewhere. Okay. And this arrow represents the shift for the time increment delta t. Okay, now what's your delta t? Well, from here around to here is maybe a sixth of a cycle. That makes sense? From this position to this position. Does that look like about a sixth of a cycle? Well, if you measure it out, you're not going to be able to hold me responsible. Okay, but it's ballpark sixth of a cycle, right? So the picture stands up to the model. If you remember pre-calculus with transformations, sine of omega t plus phi. If you do omega times t plus delta t, then you got omega t plus phi plus omega delta t, right? Well, I'm gonna apply first.
Showing what I'm doing. Don't have to. So in general, if I just want to
Okay.
demonstrate in line by minus 4x cubed, the next thing I write down is y minus 5 negative 4x cubed. And then we're going to share.
Look up transformations. I'm not gonna explain them to you right now. Again, I would if we had a little more time, but you can do this. It's probably better for you if you do. It'd probably be better for you if I included omega, because if I multiply omega times d plus delta t, I get. That looks a lot like a W, but the horizontal shift is negative omega delta t. It's just a straightforward transformation.
Sort of means like a pet string there. Want to get the help you to write this? Let me write it.
Horizontal shift of negative omega delta t that is relative to a sine of omega t plus phi. We've added an omega delta t, gives us a horizontal shift of a negative omega delta t. Now, propagation speed is c. I have stuff crossing my L's. So the wavelength is lambda equals c times capital T. Remember that c will kind of universally stand for propagation velocity. Although in the introductory problem sets, I might have still been using v. I didn't have thought to look. Okay. Lambda equals c times big T. Big T is the period. Okay. And the period is 2 pi over omega. Now this is done more intuitively. Okay, C is your distance per time unit.
Yeah, these were variables have specific meanings in the context of my problem, right? Like time and minutes and speed and mile per hour and number of items and profit for that way.
I'm going to write out what C equals. It's frequency times wavelength, which is
What is the same?
I'm writing it like a fraction, but it's not a fraction.
Okay, give me your answer.
It's distance distance per cycle times cycles per time unit. It's how far you travel in one cycle, multiplied by how many cycles you travel in a second. This is a very intuitive idea. It's not, again, not a formula you want to memorize. But it's a formula you might want to think about until you totally understand it, which you will within an hour of getting into the introductory problem set on waves. Okay? Now, what I've done is the mathematical development of a traveling harmonic wave. Okay? That's not in the introductory problem sets. Introductory problem sets will give you some perspective on that development. Okay? And it gets better. Because if you have two traveling waves, they can merge and form another traveling wave. Now, how does a rogue wave in the ocean occur? Well, you've got one set of waves created by this storm over here. Okay? And that storm creates waves this high. Okay? So it's like this. That was what the surface of the ocean would look like if you sliced it and looked at it from the side. It would be propagating, just like sine waves I drew. Okay? And of course, if it's propagating in a positive direction, you're going to want to use a negative value of omega. Okay? Well, there's more to it. We'll see. Now, over there, there's another set of waves. And they're a little higher. Not dangerously high, but they're a little higher. Okay? And they're moving at a different speed than these waves because in the ocean, what water waves, for reasons that we're not going to get into enough depth to totally do mathematically, but water waves travel at different speeds depending on how high they are. Okay? So these waves are traveling at different speed of these waves, but more or less in the same direction from two different storms that aren't, they're over there someplace, but not that far apart direction-wise. And occasionally, those waves are going to catch up. One of those peaks is going to catch up to one of these peaks and make a big peak, which is dangerous. Now, if there's a third storm, maybe even bigger waves over there, doesn't happen very often, that those three waves can join up to form a wave that nobody can survive. 100-foot waves and stuff like that. I think those have been recorded, but I'm not sure exactly where the status of that is, but 70 feet, I'm pretty sure has been recorded by buoys in the ocean. Okay? You don't want to be around, even if you're in an aircraft carrier, although aircraft carriers could handle it. You really want to know if they're coming. You don't want them to hit you from the side. They could cause problems even for an aircraft carrier. And I'm no expert in aircraft carriers, so maybe it could really cause a problem. Okay. You don't want it to happen to your battleship. All right. And you can't predict them. You don't know when they're going to catch up. Although using a little AI, it's a little telemetry or whatever they're using to measure their position, maybe you could. Okay. Point yourself in the direction of the waves if you know there are three storms out there. Or were sometime in the past. Okay. So what I'm really getting at is what's called superposition of waves. Now, we've only got a few minutes. But just like you got I'm just going to use, I'm not going to forget the example of water waves. Now, in general, if you have two waves that join up, they just add up. The Y values add up. Okay? Now, there's some mathematics here of sum of angle formulas and all that kind of stuff. I'm sure you're probably using that somewhere in your engineering courses. And you kind of got to know it. If we had a full class period, I'd work it out for you. Okay. But this equals B cosine of omega t plus phi, where B is a function of A1 and A2, and maybe phi 1 and phi 2. And the phi is some combination related to phi 1 and phi 2. Okay. And a picture of that is pretty easy to draw. Okay, so let me just say you got two waves of the same, with the same period. And one of them just happens to be nice like this. And another is out of phase with it. Okay, so say the other wave is here. Now I gotta know where to aim. I'm gonna screw it up. And it's not very well drawn. But you've got another wave, maybe not of the same amplitude, so I'm not going to draw it with the same amplitude. Oh man, the shoulder just kind of stuck. So something's a little screwed up, but anyhow. Hey, you got this wave. At every point, this means you just add this height to this height, which gives you this height plus this height. Gives you a point up here. Now, the easiest points to plot are the points where one of the waves or another is at the 0 point, because those points will be right on the other wave. Okay, so we could add this to this, and we get a one here, and we add this to this, and we're down here. We add this to this, and we're down here, and then we're back up here and up here, and then we're down here, and it's not very well drawn, but it's going to be kind of like this. Okay, not real well drawn. Now, as briefly as possible. If you've got two waves, one traveling to the right and another traveling to the left. Alternatively, you get a wave where the peaks, let's say the waves have the same wavelength and amplitude, okay? Identical waves, but one moving to the left, one moving to the right. When they merge, what happens? Well, at some point, like maybe about here, this wave will have moved over to here, this wave will have moved over to here, this peak will have moved to here, this peak will have moved to here. You gotta get a big peak. At the same time you get that big peak, the valleys will also move together. So you got a big valley. It's kind of a rogue wave, okay? But it doesn't last because you move another order of a wavelength and both waves are going to be down at the 0 point. Okay, so 0 points are going to match up. And then a little bit later, the peaks will match the valleys and the whole wave will be flat. Okay, and what you get is a wave that between any 2 points, and you could assume these are infinite waves and they've been moving for an infinite time. So at any point, you have maybe a wave that does this between these 2 points. And then it flattens out a little bit later. And then it does this a little bit later. So it's just kind of go, oh, you know, like, you understand what I mean? Does that make sense? And in between, you know, it'll have a time when it does. Yes. Then a time when it does the same thing on the other side. That's a concept you want to take with you. We'll work it out mathematically. Some of it maybe Friday, the rest of it next week. Okay? Those are standing waves. I've got a really neat demonstration of a standing wave. But yeah, we're not quite out of time. We just find the ball. Here. This is the first time I've found anything that I thought was a wire supply. I had a kind of hard to misplace them. 4.5 feet long, but I'm not seeing them. Unfortunately, I'll dig them out before. I might actually take them over to the other building. If you even had a hollow tube, yeah, that's going to have to wait a far to things are all in disarray. If you clap your hands in front of a, let's say one of those hollow cardboard tubes you use for concrete, and just if you don't know, just imagine a tube about this big around and about this high. Clap your hands, you're going to hear an echo in the tube. Talk into the tube, you're going to hear your voice sounds a little funny. Okay. Although most of what you're hearing is through bone conduction from your own voice. Somebody else is talking into it. Okay, what happens is you're sending out a bunch of wavelengths. Some of those wavelengths match up with the length of that tube. Okay. In a way that we'll describe, fairly easy to understand on Friday. Okay. So they resonate. And what you have then is essentially the wave that travels down the tube reflects off the other end of the tube and joins up with the wave that you're producing. Okay. And does this. So you hear a lot of sound. What other thing? How many of you have laptops you can bring to the lab? Can you remember to bring them? Okay. Because I'm not sure we can do it with the computers I have available here. It's very simple. You download Audacity, which is a very simple, quick download. It's been safe for 30 years, but you can check it out. Don't download it if you're not comfortable. You can check out its reputation. It's a sound editing program that we can use to detect the waves. They're made by sounds. Okay. And it has a resolution down to about 1/100,000th of a second. Okay. And since we're going to be detecting waves, have wavelengths on the order or frequencies in the order of 10,000 cycles, which is higher than I can hear. But you should be able to clear as normal. Okay. Starts at about 20,000 and goes down with age. So we'll actually be able to detect waves that most of you probably can't hear. kind of neat and really easy. Okay? So bring those laptops if you remember to do it. Or we won't be able to do that. We'll be able to do a lot of other stuff. Okay? And if you like, remember to bring the class once or twice. Just get some key data. It's pretty neat stuff. Okay. So get into the mathematics, understand the mathematics of what I've done here so far. And then think about the mathematics of how you get this into this form. At least scope it out. Okay? Something you should be able to do if you've been through differential equations and studied resonance. Maybe you didn't, because that's not always done. And it's something you're going to want to be able to do because it comes up in a lot of places in engineering and elsewhere.